Hi, this is Charles Maggio. Welcome back to our Epidemiology. In this final screencast about survival analysis, I'm going to actually introduce the survival package. At this point, after having this fairly healthy preamble about rates versus risk, binomial models versus exponential models, and going through the process of actually coding a Kaplan-Meier curve, the implementation of survival analysis in R becomes almost trivial. And if you understand this stuff, the material that came before this stuff is really just a matter of just the mechanics of implementing it. So the package we're going to use is the survival package. And in the survival package, there are a couple of commonly used functions. The first one is the serve function, which creates a survival object. So what you'll do is the first thing you'll do is you run serve on your data, essentially on your time data and the status that you're interested in, to create a survival object. Then you will create a Kaplan-Meier curve with the serve fit function. Then you can actually test whether there are any significant differences between groups in Kaplan-Meier curve with the serve diff function. We'll go through all of these, which actually calculates a log rank test, and the log rank test is a form of a chi-square test that returns a p-value for whether any observed differences are more likely due to chance or not. And then finally, we'll talk very briefly about Cox proportional hazards, but it's the Cox pH function that does a Cox proportional hazards function. We'll talk a little bit about what that is. But let's get started with doing survival analysis in R, how you would normally kind of do this. So first thing we're going to do is, just to remind you, we're going to load the melanoma dataset. We'll use the mass library, load melanoma, and as a quick reminder, the melanoma dataset is a dataset of 240 or so individuals from Denmark, I believe in the 1960s, who had malignant melanoma, which is a vicious disease. And status basically was 1, death from melanoma, 2, I believe death from another cause, and 3, survival to the end of the study itself. We are going to be using the survival library. So if you haven't actually installed the survival library, just use install packages survival. If you have it on your machine, we'll use the library function to bring it in, and it's in. As I said, the very first step in doing a survival analysis is creating a so-called survival object, and we use the serve function, and we supply to the serve function what the time variable is, the time until the outcome that we're interested in, and what the disease or death or the outcome that we're interested in is. In this case, it's melanoma status equivalent to 1. And we're going to save that as an object, which we need to do because we're going to be doing some analyses of this object. So let's create this survival object using the serve function. We do that. Now here, we could take a look at that survival function, exactly that survival object, exactly what it is. I've put a little note here saying that the sign plus indicates censoring. We'll talk about what censoring is in a moment. But here we go. This is what the survival, basically it is all the observations, the time to the outcome, and then this little plus sign indicates what's called censoring. And by censoring, it means some outcome that is not the outcome that we're interested in. It's right censoring. So basically, these are folks who survived throughout the entire study, so we don't know what happened to them after the study ended. Or they dropped out, or they had some outcome or death, for example, in this case, from something other melanoma, where there is no plus sign, and this can be a little counterintuitive. Those are the people that actually died from melanoma in this study. And you could see it yourself. Let's take a look at the original data set, the melanoma data set. We'll just look at the first 5 or 6 observations here. And what you see is, so you have the time this person was in the study for 10 days, 30 days, 35 days, 99 days, 185 days, 204 days, right? This person apparently dropped out. They were no longer followed. This person died from something else. This person dropped out. This person had status 1. They died from melanoma. And we see that reflected in the survival object, where this person is censored, censored, censored. These 4 censored observations refer to these 4 initial observations over here. We don't get to the first actual outcome due to malignant melanoma until the 5th observation. And we see here that the 5th observation and the 6th observation here don't have that little plus sign. So that's how you sort of interpret these a survival object. As I said, the first thing you might want to do is fit a Kaplan-Meier curve. That's usually quite informative. We spent a little time talking about that. And to do that, you don't have to go through the process. You could if you really wanted to, but you don't have to go through the process we went through in the previous screencast where we did our own Kaplan-Meier curve. There's a simple function that'll do it. It's called surv_fit, and we give as an argument the survival object that we created up here. And here, what you see we're saying is it's a formula, and I'm saying, okay, I just want to look at the survival of the entire group. I want to have a single curve. I want to see how this group sort of descriptively behaved over time. And so I just specify one group here with this formula tilde. And I'm saving that as a Kaplan, I'm calling it KM object. I could have called it anything I wanted. Let's run that. And if I want to see a summary of the Kaplan-Meier object, what I get actually is that table that we were talking about, where you have the time to the time to the period, the interval in which something happened, the number who were at risk at that time, what event occurred here, there was a death, and what the survival probability was, and then finally, actually, it doesn't list the risk probability, but that's fine. You could just 1 minus this is the risk probability for death in that time period. And we can simply plot that Kaplan-Meier object, which I'm going to bring over from the other screen, which is right here. And this essentially is a Kaplan-Meier survival curve. And each time it steps down, there has been a death, and the risk of survival goes down. This essentially is the risk of survival is the number of person days over here of observation. If we wanted to, we could compare two groups of people. And, survival is a log run. Yes, here we go. We can compare two groups of people, or basically look at some variable that splits people up into two groups. In this case, we're going to look, we're going to use the same function, survival fit, that we used here to create the Kaplan-Meier object. We're going to, again, use our survival object that we created up here. But now, rather than simply plotting the single group, which we indicated here, we're going to separate the groups by whether the lesion was ulcerated or not, which is a variable in this data set. And we're going to save that to another object. I'm going to call this object Kaplan-Meier object ulcer. If we run that, we can now plot that if we wanted to. And here we see a very different plot. Now it's been split up into two groups. The ones on top here actually are the ones without ulcers, the lesions that without ulcers, and the ones on the bottom here are those lesions with ulcers. We see that the probability of survival, the cumulative probability of survival, is much lower if your lesion was ulcerated than if it was not ulcerated. There are a couple of little bells and whistles we could add to that. We could add the option for a confidence interval, which is a nice thing to have. We could color each one differently so we could differentiate them a little bit more easily. And if we run that, we see the same thing here, and now we kind of see that really there was a difference. There was quite a difference between these two groups. If we want to actually convince ourselves that there was a difference between these two groups, we can calculate a log rank test, which is calculated with the survival difference, or the surv_diff thing. Now, what is this log rank test? Well, basically, it is a chi-square test. It's a contingency table of events by time points. And for each group and every time point in time, you calculate an observed minus an expected, you square it, and you divide by the variance. Essentially a chi-square. And R does that very quickly and nicely for you with the surv_diff function. Let's run that, see what we get back. And here we have the survival difference function, and we see that it gives us a little information about each of the two types of outcomes, gives us the intermediate calculations here, and in the end gives us a chi-square and the probability of a difference, and it is highly significant here. So these two groups really are quite different. Now, at this point, we might want to do a Cox proportional hazards test, or a Cox proportional hazards model. Now, what exactly is a Cox proportional hazards model? Without going into a lot of detail, because there really is just so much time we could talk about this stuff, you could consider that if you can consider that the two curves are proportional and essentially parallel, then one nice feature of that is you can exponentiate the beta coefficients, so you don't have to worry about the baseline hazards, just the relative effects. And what you end up really, it's almost like akin to a generalized linear model, but the hazard model is basically h sub I at time t, right, is equal to some baseline hazard at time t, and then an exponentiation of that of a very common b0 plus b1 x1 plus b2 x2. But basically, we can get a linear model out of time data, out of exponential survival data. And that's the Cox proportional hazards model. It's a very sort of like neat and clever approach to be able to allow us to get regressions out of time data. And let's take a look at what one might look like. In this case, I don't think we need this right now, but the function to do a Cox proportional hazards model is just called, here it is, it's just called Cox PH. And then the arguments are the survival object we created. You see how important it is to do this first step and create that survival object. That kind of trips people up sometimes. And then just simply a model, the same way we might do a regression model. So here we're interested in the linear effect of whether the lesion is ulcerated and the individual's gender. And we're going to look, and we exponentiate the risk. It's basically exponentiated like a incidence density ratio, like a risk ratio. We run that. Oh, I need to run this. We need to run it like this. Sorry. There you go. Now I could look at a summary of that Cox proportional hazards model, and here what I see is that first there's the coefficient, then the exponentiated coefficient, which is what we're interested in, and here what you see is that basically the risk for mortality, which is the outcome we're interested in from melanoma, in patients with ulceration was 4 times that. Patients who didn't have melanoma and whose gender was, I believe 0 is female. I have to look at the data here, but it's interpreted the same way you would interpret a linear model. We look at the standard error for that, and it does the standard error. If you double the standard error, it still appears to be within that. So it is highly significant. That result is actually really quite significant. Kind of nice, gives you the exponentiated upper and lower 95 confidence intervals for that. You could look at the R-square for this particular model, compare it to other models, likelihood ratio test, wall test, concordance. It's a nice little feature. So what you can see here is that it really is fairly straightforward and relatively simple to run Kaplan-Meier curves, survival curves, and Cox proportional hazards in R. The only difficult part is actually understanding what's going on in the background. And with this, I hope you have some tools that you could use for survival data analysis in R.